Current electricity for class 12. Hi, myself Dr. S.K. Busher, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students. Lesson 5 of Chapter 3 on Kirchhoff's rules. In this lesson, we will discuss Kirchhoff's rules, then application of Kirchhoff's rules in electric circuits, and finally, Wheaton bridge. Let's begin. Kirchhoff's rules. Two rules, known as Kirchhoff's rules, are the basic tools for solving complex electric circuits. This is the portrait of Gustav Robert Kirchhoff, the German physicist who fostered our understanding of electric circuits, spectroscopy, and blackbody radiation. Simple electric circuits may be easily handled by Ohm's law. Consider the following problem. Find the currents in the branches in the circuit below, as shown in figure 1. Given R1 equal to 2 ohm, R2 equal to 4 ohm, R3 equal to 2 by 3 ohm, and EMF E equal to 10 volt. Answer. The equivalent of the parallel combination of the resistors R1 and R2, which is 2 into 4 divided by 2 plus 4 equal to 4 by 3 ohm, combines in series with R3 to give 4 by 3 plus 2 by 3 equal to 2 ohm. Thus, the given circuit may be equivalently redrawn as in figure 2. Thus, we get I equal to E by R equal to 10 by 2 equal to 5 ampere. The equality of potential drops along two parallel branches gives I1 into R1 equal to I2 into R2. Since 5 ampere of current divides into two streams, I1 and I2, we have I1 equal to I2 multiplied by R2 by R1 equal to, within bracket, 5 minus I1, then multiplied by 4 by 2 equal to 10 minus 2I1. Therefore, I1 is equal to 10 by 3 ampere and I2 equal to 5 minus 10 by 3 equal to 5 by 3 ampere. Let us augment the complexity of the circuit to the next order by inserting an additional cell of EMF E dash as shown in the figure 3. We immediately realize that the problem is no longer doable by Ohm's law alone. In such cases, Kirchhoff's rules come to our rescue. Kirchhoff's junction rule or Kirchhoff's current law. According to this rule, the sum of currents entering any junction of an electric circuit is equal to the sum of currents leaving that junction. At the junction A of the adjoining circuit, Kirchhoff's junction rule gives I1 plus I2 equal to I3. Here I1 and I2 are the outgoing currents, while I3 is the incoming one. Interpretation of Kirchhoff's junction rule. The rate of flow of charge across a cross-section of a conductor defines an electric current, and for a steady current, there is neither accumulation nor depletion of charge at junction points. Thus, Kirchhoff's junction rule is a statement of conservation of charge in the context of steady currents. Let us discuss the second of the rules, that is Kirchhoff's loop rule. According to this rule, the algebraic sum of the changes in potential encountered in a complete traversal of any loop in an electric circuit is 0. We require a sign convention to apply Kirchhoff's loop rule to an electric circuit. Sign convention. We will follow the convention that the potential drops encountered while traversing a loop in an electric circuit are negative, while potential rises are positive. In this context, remember that potential changes by minus I into R in a resistance in the direction of the current, while against the current it is plus I into R. Potential changes by minus C in a cell in the direction of the positive to the negative terminal, while it is plus C from the negative to the positive terminal. Let us consider the adjoining circuit. Traversing the top loop ABCDA in a clockwise manner, we get minus I1 R1 plus E1 minus E2 plus I2 R2 equal to 0. This is equation 1. Here, the first term is negative as we have moved in the direction of the current, that is down the potential. The second term is positive as we have moved from the negative to the positive terminal of the cell, that is up the potential. The third term is negative as we have moved from the positive to the negative terminal of the cell, that is down the potential. The fourth term is positive as we have moved against the current, that is up the potential. Remark: since Kirchhoff's loop rule leads to a linear algebraic equation, it doesn't matter whether we take the potential drop as positive or as negative. We traverse a loop in the clockwise or in the anti-clockwise manner. For example, applying Kirchhoff's loop rule in the mass ABCDA in the clockwise manner with the potential drop positive convention, we get I1 R1 minus E1 plus E2 minus I2 R2 equal to 0. This equation, when multiplied by minus 1, converges to the earlier equation. What we should remember is to stick to one particular convention while constructing an equation by applying the loop rule. Also note that, if not provided, assign currents in the branches in a logical way. For example, allow current to emerge from the cell having the highest EMF. If the solution returns a negative value for a particular current, then it means that the current flows opposite to the assigned direction. You need to construct as many independent equations as there are unknowns in the given problem by applying Kirchhoff's rules repeatedly at different junctions and in different loops of the circuit. The loop rule can also be applied to a mesh containing a capacitor by treating it as a source of EMF and in open circuit under steady state condition. Coming back to the example, we traverse the bottom loop ADEFA in a clockwise manner to get minus I2 R2 plus E2 plus E3 minus I3 R3 equal to 0. This is equation 2. Equations 1 and 2 and the current equation I1 plus I2 equal to I3 obtained by applying the junction rule at A may now be solved for the currents, provided the other parameters, that is the resistances and the EMFs of the circuit, are known. Interpretation of Kirchhoff's loop rule. Potential at a point is a function of the location of the point. Complete traversal of a loop in an electric circuit means returning to the starting point and hence to the starting potential. It means that whatever increase of potential was encountered during the complete traversal of the loop must have been counterbalanced by an equal decrease of the same. Potential is the energy per unit charge. Conservation of potential is, therefore, synonymous with the conservation of energy. Thus, Kirchhoff's loop rule is a statement of conservation of energy. Let us now consider the application of Kirchhoff's rules to circuits. Question 1. In the circuits shown in the figure, E, F, G, and H are cells of EMF 2, 1, 3, and 1 volt respectively, and their internal resistances are 2, 1, 3, and 1 ohm respectively. Calculate number 1, potential difference between B and D. Number 2, potential difference across the terminals of each of the cells G and H. The currents in the branches have been represented as in the figure. Applying Kirchhoff's loop rule in the mesh ABDA, we get this equation. When simplified, it becomes minus 2i plus 5i1 minus 1 equal to 0. This is equation 1. Next, from the mesh BCDB, we have this equation, which simplifies to 6i minus 2i1 minus 2 equal to 0. This is equation 2. We multiply the equation 1 by 3 and then add it to the equation 2 to get I1 equal to 5 by 13 ampere. This is equation 3. Substituting I1 in the equation 1, we get I equal to 6 by 13 ampere. This is equation 4. Therefore, the current in the diagonal arm is, which is I minus I1 is equal to 1 by 13 ampere. This is equation 5. Number 1. The potential difference between B and D is VBD equal to I minus I1 within bracket, then multiplied by 2 is equal to 1 by 13 into 2 equal to 2 by 13 volt. Number 2. The potential difference across the cell G is the current flows out from the positive terminal of the cell in this particular case. So Vg is equal to Eg minus IRg equal to finally 21 by 13 volt. The potential difference across the cell H is the current flows out from the negative terminal of the cell in this particular case. So VH equal to EH plus I1RH, which is finally equal to 18 by 13 volt. Question 2. Find currents I1, I2, and I3 in a given circuit. In steady state, a capacitor acts as an open circuit. So I1 is equal to 0. This is equation 1 for this problem. Applying Kirchhoff's junction rule at C, we get I1 is equal to I2 plus I3, or I2 equal to minus I3 since I1 is equal to 0. This is equation 2. Applying Kirchhoff's loop rule in the mesh A, B, C, H, G, A, we get this equation, which simplifies to 5I2 minus 15I3 equal to 9. This is equation 3. Substituting I3 from 2 in 3, we have 5I2 plus 15I2 equal to 9, or I2 equal to 9 by 20 ampere. This is equation 4. And I3 equal to minus 9 by 20 ampere. This is equation 5. The negative value of I3 simply states that it is opposite to that shown in the circuit. Equations 2, 4, and 5 constitute the answer to the problem. Question 3. In the given circuit, E1 is equal to 3E2 equal to 2E3 equal to 6 volt. R1 equal to 2R4 equal to 6 ohm. R3 equal to 2R2 equal to 4 ohm. And C equal to 5 microfarad. Find the current in R3 and the energy stored in the capacitor. The distribution of currents as per Kirchhoff's junction rule is shown in the figure, where we have allowed a current I to emerge from the cell of highest EMF, E1 equal to 6 volt. Applying Kirchhoff's loop rule in the mesh BEDCB, we have 6 minus I1 into 4 equal to 0, or I1 equal to 6 by 4 equal to 3 by 2 equal to 1 by 5 ampere. Similarly, from the mesh ABCHGA, we get this equation, which simplifies to minus 5I plus 9I1 minus 5 equal to 0, or I equal to ultimately 17 by 10 or 1.7 ampere. This we get when we substitute I1 equal to 3 by 2 ampere. In open circuit, the capacitor C is a seat of voltage V with the lower plate being positive, say. Now from the mesh AFEBA, we have this equation, which simplifies to minus V plus within bracket 1.7 minus 1.5, then the bracketed quantity multiplied by 2 plus 2 equal to 0. Therefore, V equal to 2.4 volt. Therefore, the energy stored in the capacitor is U equal to half Cv square equal to half into 5 into 10 to the power minus 6 into 2.4 square equal to 14.4 into 10 to the power minus 6 joule. Question 4. 12 identical resistors, each of resistance 1 ohm, have been arranged in the form of a cube. Find the equivalent resistance of the cube across its two diagonally opposite points. Here, we may exploit the inherent symmetry of the circuit. Let us name the corners of the cube. Let a current I enter the cube at A and leave it through the diagonally opposite point G. The input current divides itself into 3 equal parts of magnitude I by 3 at A. Each of these currents divides themselves into 2 equal parts of magnitude I by 6 at B, D, and E. Again, at C, F, and H, the 2 currents of I by 6 recombine to become I by 3. 3 currents of magnitude I by 3 each finally recombine at G to flow out as I. Calculating along the pathway ATCG, the potential drop across the points A and G is obtained as V equal to, finally, 5 by 6I. This is equation 1 for this problem. If R is the equivalent resistance across the diagonal points A and G, then the principle of equivalence gives V equal to R into I. This is equation 2. Comparing the equations 1 and 2, we get R into I equal to 5 by 6 into I, or R equal to 5 by 6 ohm. Let us now come to the topic Western bridge. 4 resistors connected in a circuit, as in the figure, constitute a Western bridge network. Across a pair of diagonally opposite points, say A and C, a battery is connected. This is called the battery arm. Between the other pair of points, B and D in the figure, a galvanometer has been connected. This is called the galvanometer arm. The galvanometer has been connected to detect current. This is the portrait of Sir Charles Whiston, the English physicist whose name is associated with this breeze. The balance condition of the Whiston breeze. Consider the adjoining Whiston breeze consisting of resistors R1, R2, R3, and R4. We close the key in the battery arm. The current flows in the circuit as represented in the figure. The breeze is said to be balanced when the ratio R1 is to R2 is equal to the ratio R3 is to R4. At the balance condition, the points B and D of the breeze attain the same potential and the current through the galvanometer disappears. Suppose the breeze in the adjoining figure is in the balance condition. Then, applying Kirchhoff's junction rule at B and D respectively, we get I1 equal to I3, this is equation 1, and I2 equal to I4, this is equation 2. Applying Kirchhoff's loop rule in a closed mass ABDA, we have minus I1 into R1 plus 0 into G plus I2 into R2 equal to 0, this is equation 3. Here, G is the resistance of the galvanometer and the current through it is 0. Similarly, from the closed mass BCDB, we have minus I3 into R3 plus I4 into R4 plus 0 into G. This is equation 4. Equations 3 and 4 respectively reduce to I1 by I2 equal to R2 by R1. This is equation 5. And I3 by I4 equal to R4 by R3. This is equation 6. Equations 1 and 2 tell us that I1 by I2 equal to I3 by I4. This is equation 7. Equations 5, 6, and 7 give us R2 by R1 equal to R4 by R3. This is equation 8. Or R1 by R2 equal to R3 by R4. This is equation 9. Equations 8 or 9 states the condition of balance of a Whiston breeze. This brings us to the end of the lesson 5 of chapter 3. We will take up meter breeze and potentiometer and also work out a few problems in the next lesson. Till then, goodbye and thank you.